The objective today will be to describe some differences between the registers of the 32 and 64-bit CPU. So to do that, let's first start with the graphics. The title says IA32 Basic Execution Environment for non-64-bit modes. So right here, there is no 64-bit mode. At the top, you'll see that there are 8 32-bit registers. Let's jump over here and go down to the 64-bit graphic. You have to go all the way to the bottom to see the caption, Figure 3-2, 64-bit mode execution environment. So now to scroll up a bit, it says 16 64-bit registers. Over here, there's 8. So this is doubled not only in the number of registers, but the size of those registers. And these are just the general purpose registers. Let's take a minute to look over at the address space. This says 2 to the 32nd. This address space can be flat or segmented using the physical address extension mechanism. The physical address space of 2 to the 36-1 can be addressed. And that little blurb is not over here, but you'll see that this is 2 to the 64. When I go up to read this, it's going to say something crazy to me. It's going to say that using 64-bit mode, linear address space can be up to 2 to the 64th bytes. I had to look that up because I didn't know if I knew the math well enough to understand. We are talking 18 exabytes. Either I am really foolish and making some sort of mistake here, in which I'll count on the YouTube comments to correct me, or the max that a 64-bit processor can deal with is a huge max. So it's safe to say that no modern computer is actually using that much address space up. Oh, and also, this is not a -1, it is a -1. So the number of addresses that can be stored is actually this number, with the last digit being 15 versus up here, if you just did 2 to the 64th, it ended in a 16. Which makes sense even if you boiled it down to bytes. Right here I'll type in 8 bits. I meant to say if you boiled this down to bits. So here we go, looking at a binary number where the place value is 1, 2, and so on. There are a total of 256 possibilities here, but what's the highest number 1 byte can represent if every single space here is a 1? Well, the highest number is 255. So why did I just say there are 256 possibilities? Because that last possibility is actually the first possibility. It's a 0. If everything is a 0, 0 is a number, and therefore it's showing you a range of 0 to 255. Thus, 256 possible numbers will be shown there. So now when I Google 2 to the 8th, that's 256. Why would Intel do a -1? I assume because you can't have an address of all zeros. Or can you? I have no idea. This is definitely one of those videos where I talk my way into more knowledge. And I Googled that question, can Intel chips have all zeros? I should probably have typed, can Intel chips have an address of all zeros? And even after I looked through this, I didn't find anything really enlightening. So not to get too carried away, let's continue to compare the 64-bit design to the 32-bit design. Looks like the segment registers stayed the same. We got 6 16-bit registers in both. The flags here are called R flags, and this one is E flags, and 32 versus 64, that's pretty easy. The instruction pointer is the same in terms of the difference. EIP versus RIP, which is not rest in peace. The floating point unit registers have 8 80-bit registers, and so does the 64-bit design. And then the same number of bits for the control, the status, the tag register. Same with the 11-bit opcode register. That's interesting, opcodes are only 11 bits. And then we got a 48-bit instruction pointer, as well as a data, aka the operand pointer as well. I wonder why they call this register a pointer if it's an operand. Looks like we have the same funky named registers over here with the same values in both. So MMX is still 64 in both, XMM is still 128 in both, and YMM is 256 bits in both. However, the number of actual registers for a YMM register seems to vary. This 64-bit machine has 16 of them, while over here there are only 8. That's the same for the XMM. This says 8, this says 16. So in both cases, the number of, I'm just going to call these the funky registers, double, but MMX stays the same, 8 over here and 8 over there. So let's come up with a few questions based on Intel's description of the differences. You see they have special paragraphs right over here to describe the differences. How do I know that? Because this sentence says, though both 32 and 64-bit modes are similar, yes they are very similar, the following paragraphs describe the differences. So starting with address space, a task or program running in 64-bit mode can address linear address spaces of up to 2 to the 64th bytes. This is subject to the canonical addressing requirement described in section 3371. We haven't gotten there yet. And physical address space of up to 2 to the 46th bytes. I wonder where that number 46 comes from. Well, it goes on to say that software can query CPU IDs for the physical address size supported by a processor. So maybe this first question will relate to the diagram only. Now let's ask a question about the address space. What's different about the address space in a 64-bit? I'll just leave it at that. Basic program registers, the number of general purpose registers available is 16. GPRs are 64 bits wide and they support operations on 1 byte, word, double word, and quad word integers. Accessing byte registers is done uniformly to the lowest 8 bits. The instruction pointer register becomes 64 bits. The E flags register is extended to 64 bits wide and is referred to as the R flags register. The upper 32 bits of R flags is reserved and the lower 32 bits of R flags is the same as E flags. See figure 3-2. So let's just keep it simple here with our questions. How many general purpose registers are there? The answer is 16 right here. Next up, XMM registers. There are 16 XMM data registers for SIMD operations, so see section 10.2. SSE programming environment for more information about these registers. So that's just a question I do not know the answer to right now, and let's just write it down so hopefully I'll remember to answer it later. What is an SIMD operation? YMM registers, it looks like this author almost copy and pasted the exact sentence here, and they only had to change the Y and X. But more information on this is in chapter 14. To keep it rolling, BND registers, BND CFGU, BND status. Doesn't tell us anything about the difference here, just to see chapter 13, managing state using the xsave feature set. Well, that sounds cool enough to ask a question. What is the xsave feature set? Looks like you have the stack pointer size of 64 bits, so that one's kind of obvious. Stack size is not controlled by a bit in the SS descriptor, as it is in non-64-bit modes. Nor can the pointer size be overridden by an instruction prefix. Control registers are expanded to 64 bits, and a new control register is it called the task priority register, CR8, or TPR, has been added. Okay, so that's a good question. What is the name of the new control register? And that's the priority register, CR8, or TPR. Okay, so that's the task priority register. And our last one for this video, debug registers. Debug registers expanded to 64 bits. All right, nothing fancy there. So that would be a very quick video. Well, okay, we got this descriptor table paragraph to read real quick. The global descriptor table register and interrupt descriptor table register expand to 10 bytes so that they can hold a full 64-bit base address. The local descriptor table register and the task register also expand to hold a full 64-bit address. Alright, the question right there is just, what is a descriptor table? I just don't know what that is. So let's stop the video here. We are almost on page 69, making great progress. Today we learned about differences in 32-bit CPUs versus the 64. The biggest and most obvious difference is the number of bits, but also the number of registers that exist in the new 64-bit CPU design.